After you do your free body diagram, you would start to calculate your reaction forces, right? Because this is a space diagram. So you want the free body diagram. Now, our intent is to able to draw the shear force and bending moment for this. Now, there's a chart that I show you, which would give you information as to how each curve would look. And I found another one in a textbook which which gives more information in terms of the UDL, when the UDL is on it. And I will also try and share that with you. Um, right? So there's another one that gives some more information, but I will tell you some of the things that you need to do. This problem can be solved by inspection, by experience. It can be solved by method of section, can be solved by singularity method, and it also can be solved by calculus. All right? Singularity method has a little bit of calculus in it too, right? Once you're able to write the shear force equation, when you integrate the shear force, you get the bending moment expression, right? But I will discuss that in a lesser extent because one of the things that is crucial for me is I want you to be able to draw the shear force and bending moment. So let us draw the now. So now we're gonna proceed. So I'm gonna draw the free body diagram quickly. So let's draw the free body diagram. And I hope all my tools come up this time around with the zoom and all. Let's see if it comes up. All right, so let's get to my tools. So I'll spend a little bit of time because importantly, we need to draw the thing properly so that you can understand. So you draw it quickly. This is what you have. You probably want to draw the free body diagram over here. Let's see if we can draw the free body diagram. It doesn't matter seriously the way we draw it. So this is your free body diagram. Right? After that, your where you have your point loads. So let's put in the point loads. So we have one here, right? We have another one over here. So those are point load. Those are coming down. So those effect of those will be minus. And likewise, you have somewhere right here. You have um a reaction, and it is a roller at this point. So because there's a roller there, you have one force. And normally where you have a pin joint, you have both. But we are not concerned with the horizontal force today. Oh, that one is wrong, term orientation. We are concerned with more so the vertical forces, right? So for our intent and purpose, even if there's will be one will be there, one horizontal one, but it's going to end up to be zero because based on what we're doing. All right, so that is starting out the problem. So now we draw these and we need to label it. So let's get into labeling mode now. Let's see if we can label this thing now. I hope that I have writing features. Now do I have it? Let me try. So this is 20 up here. No, don't have writing feature yet. Hold on. So I want writing lines. I need to write in. All right, so I can write now. So this is 20 kips. All right, so kips is another unit. All right, so it's 20 kips. Okay, and then you have a reaction here because this is A and this is B. You can call this A, Y, and B, Y. All right. Now the distance between here is 30 and this one is 15. All right. So all whenever work the problem. And this is feet. All right. This is right. All right. All right. So, and likewise, you have the UDL up here. Let's put that UDL in. Now, the UDL can be converted to a point load. What do I mean by a point load? All of these, so the 20 keep coming down is a point load, right? That's the first one. And the second one and the last one coming down over here, 20. So 2 point loads coming down, right? And the reactions are point load, there are point loads going up, all right? So we can convert wherever you have a UDL, and the length of your UDL is important. So this one is 30. Now this is 4 kips per feet. So look, it is not the foot. So this is, so in other words, it's the same thing that it could, in other words, it could have the same thing, we could call it Newton meter. But this one is kips per feet. So we could call that Newton meter. So it is 4 kips per feet. So within the range across here, so that means that there is every 1 foot you have 4 kips come acting in it. Every 2, you understand me? So that's a ratio that you have. So it is 4 kips. 4 kips would equals to 1 foot. Right? So basically what it's saying is that along this part, that is it. So in order to get the force coming down, you must multiply. Look for the length, always the length, the complete length of the span of the UDL, which we call uniform distributed load. In this case, it is 30, and the ratio we have here for term of kips per feet is 4. So when you multiply, 4 kips per feet times the length, which is 30 feet, then automatically the feet would cancel and you're left with 4 times 30, which would be 120 kips. So that now gives you the force. And where does it always act? It always acts in the center, right? In the center of the section, that particular section. So if the section is 30 here, you're gonna act at 15. So you can draw it a faint line point load. So we are just showing everybody understand that already. And I'm glad. So this we right here, we know is 15. So this is 120 kips, all right? So we have converted our UDL to it. And it is important when you're calculating your reaction to always do that. So now we have the reaction. We can simply go ahead, right? So we're just going to jump to it quickly. So here now we can use our first equilibrium equation. Sum of the forces in 0. So we're going to sum all the forces in the vertical. So the first one we have is minus 20. Right? The next one we have is...
So I just choose to play Clash Royale instead of living my life.
Someone saying something? Plus AY. Alright, so this is the second one. The third one is the UDL. That one that we convert. So it's also a minus 120 kips. And then the other one is the BY. And the last one coming down is a minus 20. So right there, we have our equation in the Y. So here we can say that AY plus BY is going to be equal sign, and add these. How much we get here? So this gives me 160. So you're going to take it over the other side, you get 160. All right. Am I correct there? Yeah. They're all added to. So that's amount of force coming down, 160. So therefore, AY plus BY is going up to balance that. All right. Now, okay, we go ahead and we use another equilibrium equation. Some of the forces, you could use any one of the points. Let's say you're taking it about B in this case. So we're going to sum our forces out B, taking anti-clockwise as positive. So we continue, and now we look at the distance, and we have all the distance. So let us proceed to do it. So we're taking the forces about B, right? So we're going to start. And by the way, we could label this. We could call this probably C. I think a C I'd call it before, and call this side D. All right. So here we go now. We're going to take a moment up at point B. All right. So we're starting with the one at C first. The distance from C to B is going to be 45, and it is going in the anti-clockwise direction, which is positive. So it's 20 times 45. That's the first force coming down. All right, so that is positive. All right, the next one is the AY. So AY is going up, which is going to be a minus. So it's minus AY. Now, what's the distance from B? 30. So we 30 there. But I agree with that. All right, and all right, the next one we have is the 120. 120, remember we converted the UDL to a point load. So therefore, it's going to be plus 120. The distance from B is 15. So therefore, it's positive also. So it's going into the anti-clock, which is positive, anti-clockwise direction. So that's 15. All right. The last one, all right. The last one now is going in the clockwise direction because this 20 kilogram over there is going in the clockwise, which is minus. So it's minus 20. And the distance from here is 15, right? So it's 15 equal to 0. So that's standard. Um, let's calculate them out. You guys have your calculator there. Calculate out those for me, please. Somebody have their calculator ready. Um, so the first one, what is the value of the first one? Please have your calculator out because you'll be working with me. So that's 900, right?
Yes, sir.
Right. Minus 30 AY plus 120 now times 15. How much is that? That is
1800.
1,800. All right. Minus the last one now is what? Minus 20 times 15. That looks like 300, yes. Yeah. Equals to 0. So from there, you're simply just going to resolve these. So you have minus 30 times AY, right? You could take this over immediately, as we all know that. What is it that you add all of the figures? So you have minus 300 plus 1800. Let me see how much is that. Plus 900. So we're getting 24. So this is equals to 24. So you're getting positive 24. We're gonna go over as minus 24. And so minus cancel minus. So there, so get some space here. AY is equals to 24 upon 30, which gives you 80 kips. All right. Now, so that's the Strom equation. So this equation was really equation 2, and this is equation 1. We substitute that back in equation. So we substitute AY equals to 80 kips in equation 1. All right, and what do we get now? So we get here that AY plus BY equals to 160. And so we simply jump in, put our 80 here plus BY. And so from that, we derive that BY is also 80. So those are our standards. So now we have worked out that our reactions equals to 80 and 80. Right. Now, everybody understand that already. So we're gonna go ahead now, and I'm gonna take this figure down, Not gonna redraw it, I'm just gonna copy it. Let's see if I can copy it. Just gonna copy it, carry it down. All right, so we're gonna put it down here. All right. All right, now that we finished that, all right. Now in exam, I don't want to spend a lot of time on. So your objective using method or section is to give you points so you can know if you're on par to be doing the things correctly. However, I don't want you to be using a lot of time to be doing method or section and not able to draw it. So you must be cognizant of that. All right. Now, firstly, so we know we have the reaction and all that. We are going to analyze the problem to another level now. Okay. Now, we had converted to point load, but let's say that you didn't convert it to point load, and it was still the four kips per 4 kips per feet here. Now, if you're using metal as section to cut across this beam, and let's say that you're still using metal as section, wherever you have a UDL, so the principle is wherever you have the UDL, you know that it is going to be, so let's say, and I'm gonna combine a little bit of singularity method with this. So let's say that you had you had cut this section here in front here, right? So typically you would have do your cutting plate. You could cut these 3 places. You could cut it here, right? And you could cut it right through here. Let's say you cut it there and you cut it here. 3 places, right? In exam now, I don't want you to be wasting a lot of time with cutting the section, but it is really to derive. So let's say you're gonna consider section CA, right? So you're gonna probably just sketch it back quickly and you draw that, right? And you cut it. So wherever you cut it, we'll establish that there's a shear force coming down and there's a bending moment going there, right? Right. So the only objective for you to, so there's a positive shear, no, negative shear and a positive moment going down. This is still 20. And we consider this arbitrary distance to where we cut it, wherever. It's not necessarily in the middle. I cut it in the middle, but it's some arbitrary distance you cut it. It's not in the middle. So let that be clear in your head. All right. So what you do here, so we'd have formulate and get your first expression here. So the first expression, when it comes to the UDL part, I'm going to show you what to do. And I want to show you how 2 things you can just sit down and you could actually write the expression, the full expression with one go for the bending moment for the entire beam using singularity. But let me just, we're going to continue the method as section here. Let us remind you. So for the first one, what would be the expression? Can somebody tell me the expression? You're going to be taking moments, right? So the first equation is sum of the forces in the y, and we're going to be as quick as possible. All right, so the first one, so you look for all the forces I have. How many forces I have? One coming down and one going up. No, both of them coming down, pardon me. So you have one coming down here. Let me just clean him up proper. Look a little bit messy. All right, so you have one coming down here. All right. Let's say that you're using method as section still, but I'm going to show you a parallel between singular method of it. So so we have one coming down which is minus 20, and you have minus b. Right? So from there, so your shear force is really minus 20. So it tells you immediately on your shear diagram coming down, the first force coming down there, and this is in kips, right? Is 20. So you know that. So that's for the first section. So right there, so you have a giveaway. The next section now is you're gonna cut it. Well, let's write the moment for this section first. So using method as section for the moment part now, and we're gonna do it the old-fashioned way, just the same. Anti-clockwise being positive. So for the moment here, everybody know that you have a positive moment, so you write it back. right? And then now you could, so the taking moment here, so there's no, you can't consider the shear force, right? Shear force is gone. And we only have the 20 times x. So it is going to be, and that is what? Positive 20 times x. And that equals to 0. So your bending moment is minus 20x. Right? So you have it. So that's it. So you for your both for your bending moment and shear force. And what is the range that we're contend with here? Our range we're working with here is between 0 and x equal 15, because between C and A is 15. So you work with that range. Whatever the range is where you cut it. The section that you cut, that's the range we're working with. All right, so we have done that. All right, now to the next section. I would prefer to be able to see this. Let me put the range over here and put it to the right side. So this is 0, x, 15. All right, let's clean up this. All right, we are going to do the next, cut the next section. All right, and we're as quick as possible. All right, so you cut, just draw the next section here. So let's say that here, right, and this is the part that I want you to watch carefully, because I'm going to have a discussion with you, and just be real with me. So you're going to cut it somewhere on the section line. So this would have been C, this would have been A, and let's say suppose you cut it in AB. So the section that we are considering we'll cut it is section CB. So I mean you cut it, so we're not CB, AB, sorry. So AB, so you cut it in AB, right? So it's not, so the cutting plane line is somewhere on here, right? Now, once it crosses the UDL, you have to approach a little bit different. From now, right? You're going to use not the point load, you're going to use the actual UDL here, right? You're going to consider that that is wherever you cut it, that is the force coming down on the member, right? So somewhere on the member, that is actually the force coming down. So, right? So remember, we don't finish right the force yet. This is part of the force. But remember, the force is in what? Four kips. It was four kips per feet. Remember that. So in order to get the load coming down, we have to multiply it by some distance. All right. So from ear to ear, right? So this would have been your new x, right? And this is method section. And it's not hard to use method section, right? So we're gonna compare it and show you. Between these 2 points, you know, between here, the measurement was 15. But you know that. But we don't know the distance beyond A here. So the distance beyond A here, you don't know it. And so it's therefore going to be x minus 15. Everybody agree? That's x minus 15 there?
So you miss the force going up, the AY force.
The what?
The AY going up. You miss it on your diagram. On your free body diagram.
Oh, you mean this one? This 20 here?
No,
Oh, yeah, man. I'm gonna put it. No, you're not the one. We're not using the 120. We're gonna put it in here. So I'm explaining that before I go ahead. So the distance that you have across here, we are left with is x minus 15. Correct? You agree that this distance that we left with, some arbitrary distance, is going to be x minus 15. Yes or no? But you understand what I'm saying there? I'm gonna put it in. I'm not finished. All right? And the moment, and we'll have a moment there. So we'll have a moment, we'll have we have the thing there coming down. Why am I joining these together? Let me just separate them so you can see the cutting plane line different from this one. So the shear force is coming down still. Right? So now the distance across here, let me highlight it. I want to see it, make you see it. The distance across here that is left. If the distance between C and A is 15, then we know that the distance between these points is going to be x minus 15. So it's x minus 15 would give us the actual force coming down now. Everybody agree with that? Right? Hello?
Yes, sir.
And the distance that your UDL always act in the center. So the fact that it always act in the center is you have to have another x minus 15, right? Upon 2. Because it is going to be halfway the distance here. Let me highlight it. So it's going to halfway, right? All right, so that's one way to approach it. This is one way. All right, so we're gonna write it that way and tell you another way after we finish this. So I'm trying to explain it in details. All right, so this was a parallel, and you guys need to understand that with your UDLs. So we have the 20 kips here, and let's go ahead now and write our moment for this section. So the moment, now let's write the shear force first. So your shear force is equals to minus 20, and this other one coming down, which is going to be what? Minus 4 times x minus 15, right? And oh, we missed something here. So we miss one going up right here. So this is what you're saying that I missed up, the 80?
Yes, sir.
Okay, thank you very much, man. All right, so we have the 80 kips right here. So the 80 kips is going to be, so it is going to be a positive 80 kips, right? All right, so right there, so in this section, so this is going to be your shear force equals to 0. So from this, you have an expression now. What have we missed out? The shear. We don't put in the shear. So the shear over here. So let's write that good. So we have the shear. Let me just quickly clear it up. So let's put back the shear in there. Nice and neat, looking good. Clean him up. So we have the shear there. So let's put him back the shear. Plus V. Right, so we have a shear coming down. So the shear is minus, sorry. Uh-oh, why did I write that as plus? Let me just fix up over here. Again. So it is minus V equals to 0. So that's a quick equation. Once you have experience, you can quickly write it. And so your V is really gonna be equals to what now? 60 minus 80 plus minus 120. You bring the V over, you have 60 minus 4 x minus 15. And we don't have to simplify that. We can work with that. What are the range that you're working with right here? Right? And you're done. What's the range you're working with there? So your range you're working with is x is between what? These 2 points. It's going to be between 0 and 45. So between here so was what? 30, and that is 15. So it's going to be between, so the range you're working with is going to be between 15 and 45. Right? And you're done for that section. All right. The last section. So you see how quick we are finished here, so right. Let me write the last one, and then I'm gonna have a discussion on it. So the last section you would have write it back again and put. Let's redraw this quickly. So you would have put back your force here. You put back all your shear here. If you choose to put back all your shear, the load coming down the center is going to be 4 times x minus 15. You know that already. That's now changed. Somewhere along here, you're going to cut it. So this section was C. This was A. You had a reaction here, 80. You have another one here that is 80, so it's 2. And you cut it somewhere across here, so you have a shear coming down, V. You have a moment coming up, which is M. All right. Yeah. All right. So here you can simply write your expression, and this is our section. Let's put down the section that we are concentrating on. We are concentrating on BD. So this is section BD. And the range that we're working with is between what now? 45 and x equal to 60. So 60 is the end of the beam out here, so it's 60, and right here, so it's 45. So that is it. So you cut it arbitrary distant there. So your x is typically going to be coming down to your cutting plane line. Right? So you're gonna write your quick expression here for your force. Let's write it down here. Sum of your forces plus 0. So identify all our vertical forces. So we have a minus 20 coming down, negative. We have one going up 80. We have another one going up 80. And we have one coming down for the UDL. And you're always gonna write it, and this is x by the way, and you're gonna write it as negative 4x minus 15. Right? And the last one coming down is a minus v. So that now, it simplifies to what now? So your v, carry v over, you're gonna get 80 and 80 give you 160, so you get 140. So positive 140 minus 4x minus 15. You don't have to simplify it anymore. That's good enough. All right, your moment now might be a little long. What if I could write it somewhere underneath here? So your moment one, sum of your moment, clockwise moment positive. Let's try and write it underneath here. So your moment one now, let's take moment. So what you knew before, you're gonna have to put them in. This was 15, right? So everything that you had before, you have to repeat. So the first one, you are taking moment. So the first one is going to be 20 times x. So you get back the same thing that you had before. So this was positive 20x. Because so that would be a what now? Anti-clockwise, right? And the next one would be clockwise, which is minus, going to be 80 now times what now? This distance here is what? 15. So what's that one? But I want to remind me, what was that one? Did we find it? Did we find the moment for the second one up here? Or we only find the shear force? Hold on, I'm not seeing.
The only shear force with this fine, sir.
Only shear force. Hold on. Let me see if I can get only shear. Let's try the moment. Let's do the moment one. Let's do the moment. Let's back up and do the moment one up here. So the moment one would have been sum of a moment. So your moment here would have been, so let's take the moment. So it is going to be 20 times x. You're gonna get positive 20x. Right, let's take off that. Let's fix that. Let's rewrite that. All right, let's go again. So let's say that you're writing, so the first moment you have a positive moment, you write it down. Then the next one would be a positive 20x because it's 20 times x, your distant x. And then now the next one would be the 80 now. So the 80 is going to be minus 80 times, remember it's going to be x minus 15 for that section, right? Because remember, it is x minus 15 for that section there. So if this is 15, right? So it's x minus 15, right? That's what we got there, wasn't it? What would you have there? So it was time 15. Sorry, time 15. Why would I get x minus 15? It's time 15 for the first one. That the distance is 15, right? Isn't this distance 15? The distance is 15 there. So it would have been x minus 15. Pardon. Everybody see what I'm saying there? So it's x times 15. You see the 15? This is 15 here. Right. Then for the next part, and that would be anti-clockwise. So the next part now is where we have to have it is going to be positive. So the first shear for your bending moment, your first shear is always positive. This, right? If you choose to cut it two places on the beam, one will be minus. Let's say you consider the shear at the front of the beam and the back of the beam. The first one we normally write that as it's normally going to be positive. But this one, it is coming down, so it's coming down here, right? So the distance, remember we work out the distance already, that it is going to be what? X minus 15 for that distance there. So it is going to be force, what was the force again? 4x minus 15 minus 15, pardon me, not 5. So that was a force, right? Because right along the span of it, and then now it act from the center. Anywhere along the span, it always act from the center. So you can literally, anytime you have a beam, it's always going to be half of that distance. So if this is x minus 15, so it's going to be half of that distance. So you can literally, for every problem, it's going to be just like this. Only thing will be different in your other problems is the 15, the distance. Once the span is before the first load is 15, whatever that distance is. So it's 15 from that x, and half, and you're going to always multiply it by this. This is almost like if you had the shear force, you integrate it and you would get the same thing here. All right, so it's a standard thing. All right. If you use singularity method, this is exactly what you would get when you integrate the shear force. So if you were to integrate this, in a sense, that's what we're saying that you would technically get here, right? Because one of the things that you remember, so let me write that and then I come back to the integration. So, so let me finish up down here, because that is, so we're typically that equals to 0. So you would have reversed the order for everything here. So for your bending moment. So all of this would come over now. So this will be coming over as what now? Minus 20x. And the 80 times 15, what did that work out to before? Didn't we work, how much was that again? That was what, 900 or something, 1200? So the 1200 is going to come over as positive 1200. Right? So that's positive 1200. Right? Oh, by the way, there is an error. This distance here is what we said. This distance coming up here. Let me just make sure that our distance. So the distance here is x minus 15. It's not. We didn't put x minus 15 here. It's 15 we put. It is x minus 15. Pardon me. Let me just fix that. So it is x minus 15. Right. I think I'm probably tired tonight. It's x minus 15. So let's explain that. Let's go and explain that to you guys. So remember now, this distance in front here was 15. But you want to get the moment coming down from this section. So let me explain it. So it's here now. This is the distance between here to here. So the distance you want, look, is moment you're taking it from where your cutting plane line is. So this distance is not 15, it is x minus 15. This, let me see if I can put it in red. So this is the distance. That is the distance. So that's why it is x minus 15. Anybody want any clarity there? Any clarity there? Everybody good with that? So right there says x minus 15. Hello?
Sir, go over it again, please.
Let me just clear up that. So is moment, we're taking moment from right here. Right out here, so we're taking moment, right at the cutting plane line out here. So this distance, we already established that it was x minus 15. Right? We established, don't you remember that? So the distance to the 80 force is x minus 15. Because this is 15 over there, but this is x. So the difference between it and x. If x goes down to here, then this distance must be x minus 15. Should I clean that up? Make it so that you can see it again. See, so that distance there, what is that distance right here? So that I clean up. You remember that little distance there? This
Sure, what's
distance,
15?
didn't we establish that this distance is x minus 15 because this is 15 and this x run all the way down here. Pass the 15, come down to this cutting plane line. So this distance is x minus 15. You remember?
Yes, sir.
Yeah. So this is x minus 15. So it's good with labeling and looking what we're doing, okay? So I was just trying to write it in around my head, but I just look to the point and show you. So it's coming from right here, you're cutting. So this distance is x minus 15, right? All right, okay. And as I said before, there is another method that can be used, two other methods, integration and singularity method, right? But most important thing, you just need to understand one of them. And the quickest one, I think we have exposure to this one already. I'll show you singularity in a second. So this is this part here. So that is the expression, and I'm just simply kind of write it here. So this is going to just take it over the bracket. I'm not going to simplify it. So this is going to be coming over as what? So I'm going to take everything over the bracket. This is minus. This is going to be 80. X minus 15. And this can be simplified. This is going to be 2 into this. You can just say that it is going to be minus 2 times x minus 15 square, right? And leave it like that. I'm not going to simplify it. All right. Did I finish right down here? Let's go back and finish right here. So we already established that this is x minus 15, right? So here we have, so this is x minus 15, right? So we're writing the last one now. So that one is x minus 15. Okay. Right, which are point. What about the distance from what about from here now? Here to here. What is this distance here now? Who can tell me the distance from right there? Because we need the next 80. How many forces we deal with so far? We deal with the 20, we deal with the first 80, we deal with we don't deal with the bending moment yet. So the UDL force, let's deal with the UDL now. The UDL is a positive one. So it is 4x minus 15. That is a force. What's the distance? We just did it a while ago. What's the distance? What's that distance there now? Coming from the cutting plane line. What is the distance of this from the cutting plane line? Out here, so. This is right here. What's the distance right there? Who can tell me quickly? Are you seeing it?
So x minus 15 over 2.
Right, because we had established it x minus 15 over 2 because, you sure? You sure it's x minus 15 over 2?
Positive, sir.
Okay, all right. So it's x minus 15 upon 2. And it's always going to be like that. And look, so you see the first part of the beam, A, that is a positive where any UDL you get, you to the front up to here, whatever distance is, if this is 15, if this is 15, or let's say it was 5, it will be x minus 5, x minus 5 times x minus 5 divided by 2, times whatever value the UDL is. That is it. For any beam you do. So I'm going to show it, write a formula, show you shortly. And for the last one, you do typically the same one if you're writing it by singularity method. All right. We're not finished yet. We have one last force to write. The last one would be 80. What's this distance here now? Who want to tell me that distance here now? What will be the last one? And that section would be, what do we call that section a while ago? BD. What's the section for BD? Hello? What's the section for BD? Are you with me?
Sir, would it be x minus 15?
Come again?
X minus 15?
X minus 15.
Or
No. No. Come again. Let me see if you say if you're right. See, you say it is x minus 15. It couldn't be x minus 15 for that distance. Don't we know the distance? We know the distance coming down here. Right? So this is what? This is x minus 15 to here. This is 30. You know that this is 30. Do you know that that is 30? Not true. You remember that?
Yeah.
So that is 15 plus 30, and this is x down here. So you have to take all of that into consideration. Now, so it's going to be the difference between what now? What's it is up to this point right here says what? 45. Don't you know that definitely? Not true?
Yes, sir.
Yeah, man. No 45 that. So 45 says 45 for that distance. Right or wrong? Anybody differ on that? Anybody don't see that? Who don't see that is 45? Why is it 45? Right? So it is here. Look, here to here is 30. Up here says 15. So you had 15 plus 30. The total distance coming down is this distance here. Can I get a different color right? So it's right here is this distance. So that is x. The distance between here and that is going to be x minus 45, which is clear. So to get that moment, it must be x minus 45. And it is what? It's not plus, it's minus. What kind of moment is it giving me? Is it clockwise or anti-clockwise? It's minus, right? Both of them are minus. Both of the 80s are minus, right? All right. So, and that equals to plus the m. Did we put the m in? Plus the m that is always there. See it out here? See the m here? Right? But, right? So the critique is that this method is a long method. Some people critique it and say it's too long for you to use method of section for the beam. So there is another method named singularity. Don't know if I have enough time to go through that, but I will at least need to write a formula expression and show you the singularity method. So, but there is a simpler method, right? So far we have written the expression. The important thing now is that you need to know how to draw it. So before I do that, let us quick time. We're gonna copy some information, go down. So let's write out some stuff that we garnered from. Let's get a sheet, right? And we're gonna write down what is it that we got. So let's write down, recall everything that we wrote. Just for clarity, I'm gonna rewrite them down here. You would have gone ahead and sketch it already, you know. Right? But I'm gonna write. So the first section we said that our this section was CA, and our range that we're working is between 0 and x 15, right? So it's less than or equal to 0, right? And less than 15. So, and therefore your shear force expression was minus 20. And that was what keeps. And the moment was minus 20x. So those are your values there. For the next part, section, what do we call that again? We call it, for the next, so we have CA and we have AB. So AB now, AB was over here. So our expression, let's write down an AB expression there. So this was AB. And AB was between the 15 and, so I'm just writing down, and it was between 15 and what, 30? But they follow?
Yes,
And,
sir.
yeah, man. And the expression we got was, see the expression here, we're not even, we could simplify it, 60 minus 4x I think when it's simplified, you will get something like this. I think V would equals to minus 20 minus 4x when it's simplified. But you don't have to simplify it. You don't have to simplify it because you're not gonna have time to that. You just need the expression and just drop a form, so what you do, you're gonna drop the limits in it just to check while you're sketching. So it's guide you while you sketch. But I'm gonna show you, I want to sketch it and show you, I want to sketch the shear force and show you how to use the information from the shear force alone will give you the BM. All right. So let me just quickly get to this part. So where are we now? Where are we? We wrote that one and we want to write the bending moment expression. So the bending moment expression, you would have worked out and got something like 120x minus 2x squared minus 1650. Right? And the last one, right, made on a section. For the last section was, what did we call it? BD, right? So write down that one too. And the range was between X was line between 30, so 30 and 6. Was it 30 and 60? Trying to remember. No, what was the range again? It was between 45 and 60. Up here says 45. It was BD. So it's 45. Let me correct that. Let's correct that. So it's 45. Oh, hold on. So it's 45 x 60. All right. And our expression that we got was V is equals to what was that expression? Let me just make sure that we write the correct one. Was the last one what? See it here? Oh, it was 140 x minus 15, something like 140 x. Hold on, let me fix that one. The 140, trying to see the value. 144x minus that. Is that correct? Let me just check that. Something is missing from that. Let me just check. Was that what we simplified to? It simplified to this. Okay, 140x minus 15. All right, cool. All right, and then the moment one now, we didn't simplify that. We just had a what did we get? 20x. All right, we'll actually just carry it down, you know. But let's carry it down. All right, and paste it. All right, so this is it. It is square though. Let me rewrite it. So it's minus 20x plus 80, because I'm not simplifying it. Don't have to. 2x minus 15. Yeah, you're not gonna have time to simplify. So don't try and simplify the expression. If you get the expression, don't bother simplify it, because it's going to waste your time. You don't need to simplify it. You guys understand what I'm saying? Don't try and simplify these expressions. Just work with them. So if you have a substitute of value in them, you substitute it and move along. All right. So this particular one that I'm doing is a little bit lengthy. You have ones that would have been much shorter. So the range when you substitute in, so for both of them, let's deal with the shear first. We're gonna draw it now. So I'm gonna take the figure. I want to take the original figure. Let me use this one. I want to copy it. I'm going to select it. See if I can copy it. I don't want to move it. I'm just going to copy it. All right. So let's just draw it now. Do we have enough space here? Let's see if I can get enough space here. Do I have enough space on it here? All right. Let's try and see if I can drop him somewhere. All right. All right. Not bad. All right. So I want it big enough so we can. All right. So that is that. Now you have this, right? All right. I'd say that I was gonna talk to you about the singularity. Let me before we talk about singularity, let us sketch the axis. Let me see if I can. So singularity is another method. You would just write the bending moment, shear force. You could actually you're gonna write the bending moment straight with singularity method. And then you could differentiate it and get back the shear force and so forth. All right, so that's that. We'll draw another one. All right. Let me tell you something, class. My intention is for you to understand how to do it. So I'm not gonna give you a lot of marks for the expression. So do not waste your time with a lot of marks for the expression. If you know by experience how to draw it, work it out. If you can draw the shear force, get the shear force diagram and get the bending moment from it. I just understand how the right, because there's some standard things that you by experience you will know it. So you don't have to waste time, and I don't want to waste time with it. So these distance we already know them. This is 15, this is 45, this is 60 out here. Right? This is 0. And that's the same line can be transferred into the next diagram. So you don't have to draw it 2 times. So it's good you keep them in line, ideally. So you just sketch one like the other. If you're trying to do it otherwise, because I'm sketching and not a draw. All right, so the first one, let's examine it here. So I'm going to explain something, then we can talk about singularity method after. Here now, because there's some condition with singularity method that I'd have to go through, right? I probably can send you a handout on singularity method. Show the formula and all right. But it is a little bit straightforward, but it have some things that you have to bear in mind. Some conditions for the brackets. All right, here now, here you are. So this is the shear force. So right there, you see the shear. Let me draw it in red. So right there, and it is minus. So you don't have to go anywhere. You see that it is a, because remember, this is your shear force diagram where you put your V, and this is where you put your BN. So right there, so this come down to minus 20. Don't know for you. It's supposed to be a sketch. Maybe I gone down too far already. So but it's a minus 20 there. So right. All right. So that's the first one. Then now you want to know what is the next point. Once you see the area over here is a simple support beam. It is not a UDL. So it means that you must get a straight line here, so like that, to the next point load. So the next point load will be right here. Remember I said this is, here is 18. I remember this one here is 80. So fact that those are 80, you know it. Now without even, so once you know so that is minus 20, I can draw the shear without even having the expression and look back at it, because look, right here, let's have the discussion right here, so now, and talk to me. You see, because this is 80, this is a minus 20 here, so already. So you know, so a minus 20 is right here, so. But you have a 80 go up. So the difference now, I can know where the line, first thing I know, the line is gonna go straight up, because see the other load here, 20 kips, 80 kips. So the difference between 80 and 60, what is that? The difference between a positive 80 and a minus 20 gives me positive what? 60. So you know, so it must come up to 60. Everybody see that? Anybody don't see that? It must come up to 60. So the distance between here and here is 60. So it must come up to 60. So it stop right here. So you see, I don't even have to look back at my expressions. Now, all right, when I reach here, so now the other part of the problem is where now I may have some challenges. Now, here so is the next part now. This is 60. I hear that it is a UDL. So the UDL, luckily you have the expression for AB section. So let's look at it for AB section. Let's get a different color right now. Blue. So look, this is your expression. So when it is 15, what is the value? So you could put in here, so when x, so you could say when x equals to 15, what is your shear force? That is the objective of it. So it is minus 120 minus 4 times 15. And immediately you get 120 minus 60. So you get the answer. What is that? You get what you get. You get that when it is 15. See it convert, see it show it back to you. So when it is 15, it is really 60 right here. So it confirm it. But what about if you put in 30? If you put in 30, when x equals to 30, you'll get v is equals to minus 120, 4 times 30. All right, that's expression, and remember, 30 times this, what are you gonna get? So that is 4 times 30. Is that correct? Something is wrong with our expression. Just checking. Which was that? What was the range that we're working with? It's not 30 we're supposed to be having for that range. It's 45. AB was 45, eh? It wasn't the only B was 45. It's not 30 is that range supposed to be writing. It's 45 range you're supposed to be working with. So our range that we put there. So
No, sir.
yeah, man.
AB supposed to be 15 to 30.
It says 15 here. So it says 15 and then this is 30. 15 and 30 is 45. So over here says 45. So the range we should have is 45, not 30. All right. So let's put in that value. So it's minus 120 times 4 times 45. What's your calculate here? So now, so 120 minus 45, 4 times 45 is what value there again? 4 times 45 is how much? 180.
Yes, sir.
And you get minus what? Minus 60. So what it is telling you, all right. Now, guys, look. Once it's a UDL, it's a slope. Remember, the principle is when it is simple supported is a straight line. You get a rectangle section from it, in other words. See there? For this part. That is a section right here, so. So there so is a single, it is a simple section for that. When it is a UDL, which is right here, it is a slope for your shear force diagram. So you need to put in a slope, and it sloped down to 45. It tells that when it is 45, it must slope down to minus 60. So identify minus 60 down here. Minus 60, I'm just sketching. So minus 60 is probably somewhere right down here. So I'd probably not join it to scale. So I probably carry the point down a little bit too much. Let me carry it up a little bit just to make sure that I have space. So let's say your minus 60 is there. So all you have to do now is draw from the positive 60. You have positive 60 and you have minus 60 down here. So you draw the line and it's a slope. We don't know where it crosses, but we know say it's supposed to connect straight line. That is it. That is simple it. All right? Okay. When it reach minus 60 now, let me change my writer. When it reach minus 60 now, so I explain. When it reach minus 60, so this is minus 60 plus positive 80. How much is that? Because look, this is 80. So you have a point load going up from this point here. And it's going to go up. Positive 80. So it is 60. Positive 60 there, so reach 0. 60 and negative 0, right? So it must go up to a minus where? It go right up to a minus 20 there. Everybody get that? So minus positive 20. Who don't see that? Any question right there?
No, sir.
Sure. So you get it because look, it's a slope, you know. All right, it's a slope. So it's a positive 20. Right up to here, so. Right. Now, I don't have to go back to the graph. Do I need to know how to close out now? If this is positive 20 and I have a minus 20 coming up, what is happening? I don't need to go back to do any graph here, so by experience. Look, if here says another simple support beam, this is automatically going to be a straight line coming out to here. Argument done. When it reaches here, so positive 20, it's positive 20 and a minus 20 coming down. Because remember this point load coming down right here, so. So see there, that give you what? A 0. So it must come back and close out at 0. So you don't have to even go back and do anything. You don't have to use you don't have to go and use this expression. If you put this expression in it, it's supposed to give you minus, depends on where you put it. If you put it 60 in it, you get 0. If you put 20, if you put 45 in it, you're going to get positive 20. But you can check that out. Right? So that is it. So now, the trick about the next section, once you know this, guys, once you know this, once you know these areas, what area is mapped here? Question I want to talk to you. What area is that? Rectangle. What area is this? Triangle. Now this is also a triangle. What area is this? Rectangle. Now the principle behind shear force and bending moment is that the area under your shear force diagram give you bending moment. So let me write that down. So the area under your shear, let me just write, I'm going to write it abbreviated. Don't have enough space. I'm going to write SF for shear force equals to bending moment. So let's do it first on. So right, even before I do any calculation, I don't have to go to the formula. I'm just going to do it by experience. Look. So the area underneath this is maps a rectangle. What's the rectangle I'm mapping here? So the rectangle I'm mapping out here, so now it maps the rectangle fully here. And this rectangle, the length is 15 and the height is what? 20. But it is a minus, yeah. So when you calculate the area, so the area for the first section, area for what we call that? CB is a rectangle. This is 15 and this is minus 20. So this gives me 15 times minus 20, give me minus 300. Kips per feet. So therefore, what is that saying to me? And this is a simple support beam, right? It is for a simple support beam. So it means that I am going to get a slope. So this is 0 for your bending moment. It means it need at this point is a minus 30, minus 300 down here. And this is for a simple UDL. For there's no UDL here. There's a simple support beam. You just need to get a slope coming down. Let me just draw that back in green for clarity. So see here, that's the first one. You also know, before we even do the middle part, let's do the end part. The area here says also going to be what? A positive, is it a positive or a negative 30? Look and tell me. It's going to be a negative 30, but it's also going to be a 300. There is a 300 for this section also over here. Everybody see my pointer? For the last rectangle is also the area there is 300. Everybody see it? Hello?
Yes, sir.
This says going to be 20 times 15 also, but this one is going to be a positive 300. It says positive 300. Well, the area is, this is just the area you want. All right. All right. The next one, the next part here. This part here, you see for this part now, because it is, you don't know where it crosses 0, so it's a little bit, you have to have experience here. What you can know or be guided by. So you don't have the actual distance with these areas, unlike the one before. What's happened to the pointer? I'm not seeing it. Where is it, Lord? I can't see my pointer. Oh, because it's green, in time it's green. So this here, we really don't know we don't know where this one stops. All we know is a triangle. All right? We can assume that it's in the middle. All right? I mean, yeah, we could, I mean, look, based on how it looks like it is, it's balanced. So it's possible 0. Let's, 15 here. So we'll just check it. If it is 15 here, let's just check what is happening. If we say that it was 15 here, right? But we can check you can check, you see, this is why we get our equation, because we don't really want to guess too much. But if you go into your expression, you would have find it quickly. So if you want to find when the beam is, how much is that measurement? 15 plus 15, 30. So for AB section, if you put 30 in AB, you know what your shear force is supposed to be. Let's put 30 in the shear force here. You're probably gonna get 0 right here. Let's put 30 and we check it. So if you put 30 in it, so AB section, so we're just checking for AB section, and your shear force equation was 120 minus 4x. So when x equals to 30, let's check and see what value we get. So it's 120, because that range was between what, 15 and 45, not sure? But remember, it was between 15 and 45, between this is 15, this is 45. So this is why the equations are important, because you don't want to guess anything. All right. So here now 15, 45. So what you do here, drop this in this expression. So it is minus 4 times 30. So guess what? It's 0. You see that? So right there, so you see that at 30, because look, the distance from, can I get a different right? Let me use black. Distance from ear to ear is 30. That then up here, so it's 30. So therefore it is 0. So it is 15 here and this is 15 here in this case. All right, what's the area of the triangle now? So the triangle there that we are concerned with, we'll just show you before we even go to the formula, because we don't need it, you know, but we're going to just show you. So the here now, what is the height here? So this is what? 60 by 15. So this is that, and this is 15. What's the area of the triangle? It's half base times the perpendicular height. So it's half, the base is what? 15, and the height is 60. So that gives me 30 by 15. How much is that, guys? How much is that? 30 by 15. How much is that? 450? Hello? Are you with me, guys? Are you're sleeping? Hello? Anybody here with me? Are you all gone to bed?
Where is it?
Well, you're not talking to me, you know. All right.
Yes, sir.
Well, I don't like someone to work hard and tired, you know, and just can't talk to me at all. So, all right. So what I'm saying here, this is 300. I want to know what it is over this side. Right? So it's supposed to be coming up somewhere. It's supposed to be somewhere over here. So when it is, so we know that it says 450. So let's map where 30 is. So 30 is right there. So this is 15, this is 30, this is 45, and this is 60. So look, it's telling us that it is 450. Positive 450, because this section is positive, remember? So positive 450, look at it now. So minus 300 plus positive 450. How much is it that we get in? 150. But now remember, for your UDL, anytime I see UDL is a curve, so it must curve up to the 150. Positive 150. You see it? And not even using the equation. If you use the equation, if you put it in, so if you put it in your bending moment, if you put 30 in this expression, it's supposed to give you 150. right? But you don't even need to do that. You just need to look underneath. Once you draw the shear, you automatically know the point. All right, so the next one, this is also going to be what? What is this value here? Can somebody tell me the next triangle? It is also going to be 450, but it is negative 450. Negative 450, negative, so it is 150, positive, negative 450 and 150. How much you get here, so? The minus 300. So that means if you put it in this expression, at what? 45. If you put 45 in this, it should give you back the minus 300. So you don't have to do that. So it comes back down to minus 300, right? So minus 300 somewhere right here, minus 300. So it comes back here. And my drawing here is not perfect. It's supposed to be a better curve, right? It's supposed to be curvy like the other one, right? All right. Now the last part, it is minus 300. What is the area of this triangle? This area of this triangle is also what? How much did we get the area of this triangle to be now? So it is going to be, the area of the last triangle is what? Not 300 too. So if you have minus 300 and you have positive 300, right? You notice I'm not even using the equation, we get 0. So it must go back where? So the line for it must automatically come back right there. And that is as simple as it is. So, right? So that is simple as it is. So these areas are minus. This area is positive up here. All right? Any question?
No, sir.
Right. Right. So here, remember, so this is 15 right here. So all right. Now, you could have used singularity to do it, right? But singularity method, I must warn you, it has some conditions that you will have to be willing, and some of you maybe don't even have the time to go read up on singularity, because I'll have to give you some condition to match it with singularity, right? And that is a challenge why I didn't really use the singularity method. But there is a singularity method, right? And there is a standard expression for when the beam is a simple support beam, not a UDL, right? And see if I can write that expression for you. So it's typically, I probably have to, I'm going to try and find the standard diagram for you. So it says that the moment would give you R1, which will be the first one, X, and it use some special bracket here, right? You notice the bracket that it's using? It says for certain condition, you would move these bracket to the regular parentheses bracket, right? But this is our, so this is a straight moment expression, but this expression that I'm writing here now is so when you have a moment on it and point loads alone, right? So these are when you have a moment and point loads. 0 here means that it is 0. So when you integrate, that is when it becomes 1. And then the next point load, so you have 2 point load, for example, right? Minus, right? So this is typically this is one way to write it, right? That is one way. Now, for our beam, you would write, I would recommend that you write up to, where is it? Up to, you see between here to here, you could write an expression up to here because that is what would suffice. You see, between here, you could write an expression, right? Let me put back the I want the diagram. Let me just copy this. I'm gonna put back the diagram here. Where is it here? I want to select a region again. So I'm selecting this. Copy it here. So that is for a single beam. So this is for a simple beam. Let me get another page. Right. So for the singularity one, right? I'm just gonna show you and write an expression for you. So what you typically write here, because so the formula would be modified a little bit for when the UDL is on it. Still don't have a right on it. So the UDL, so it's saying that the moment, and you call it the moment with respect to x, right? And typically you could also write the shear force first. And if you integrate the shear force, you'll get the bending moment. But I'm writing a typical one. So it says any load first that you have, we call it RA, right? So this is a standard formula. You'll have to modify it as you go along based on what you have in the expression. P meaning point load, X minus D. So what they do, typically they start up here as call that D. Then you would call maybe the next one coming down here. So we'll label it the other way around. A little bit too. Let me get rid of this expression. So let me just clear this. So typically you have different ways, right? So I'm gonna show you the formula, but it would have to be modified. So between here and the first point load we call D, we start typically from down here. So down here, let's say that you're cutting it between, this was what? This was C, and this was what do we call that? D. So they call that first D. The next cut you would make is probably right here, right? So that will be first cut. The second cut to be here. Or since it's 3 cut, then probably you could call that C, B, and call this A. Right? Let's say that you cut the beam in 3 places. So you would typically call it that. Right? So I've kind of modified. So based on what you have and what you need to cut. Because just 3 cut you really need. So so that formula would be modified to look something almost like this. So you would put R AX, right? Mean your first point load. But your first point load will be really here, right? So it's the formula is looking something like this. Rx plus, if you have a point load, whichever point load you have between any point. So you have a point load at C, so you'll have X minus C, right? And then you would have the next one now you'll have, all right, you see right where the first load UDL start, you're gonna have that one as minus. This is minus, and we call up here double. Some of them just symbolize that as double. They use the UDL as double. So let's call that double. And the distance across the span, right? So for the first cut, let's say you had cut it in the middle. All right, if you have cut it in the middle, then you know that it will be half whatever distance. So we're gonna call your distance there is B. So you could call that X minus B. Right? So remember now, the C would be the differentiation between where you cut it. Right? The formula might mix you up. Let's see if I can regularize that formula. So in this case, your your first cut would be really the difference between where this distance is. So this distance would typically be like your x, right? For your first cut. This would be like where you're 15 here and you cut it to some distance down here, right? So I call this 15. I'll typically put 15 here, but I'll just put C here just to, yeah, put C. So where you got your first cut, put that C, just symbolizing it for you, right? And then now you divide x minus C, so it will be x minus C upon 2, right? Which you have here already, because it's half. So the distance is going to be x minus C, whatever distance C is when you cut it, and then it's half of this distance. So in other words, you could put this underneath here, it's the same thing. So it's x minus C, and then the next one, let's say you cut it out here now, where we would call that one now B. So you would have plus omega times x minus that one is now what? B, so it's x minus B times x minus B. And you have the 2 over here already. See, the 2 would come underneath here. It's the same difference. If you want to visualize it, see there, right? And typically that's an expression for it. So that would give you your, this is your moment, your bending moment expression. And if you want the shear force, right, typically what you would have to do, you would have to differentiate. So you'd have to go dm upon dx. When you differentiate moment, right, when you differentiate moment, you will get your shear force. So your shear force would result to you something like RA, right? The bracket you had here was 1. This was 1. So this would typically get P to, but these brackets are not round brackets here. These are really these brackets, because they are conditioned why they put the brackets that way. So it is C, and you differentiate that, that becomes 0. And when you differentiate this, you're going to just get back your UDL. So it is going to be x minus C, right? So that's typically what you would get, right? So you would get just 1. Remember, this would be 2, but you will get 1. Because remember, x minus C square omega Z upon 2. When you differentiate this, you would take away 1 from that, multiply this by 2, right? So typically you're going to get these are cancelled. So you're going to left with omega x minus C, right, to 1. So that is what you will get here, minus, and then this one will be plus when you finish, x minus B to the 1 power. Still keep the bracket, because there's some condition that when the expression inside here, if it becomes minus, it drops out, and when it comes 0, it drops out. So there are some conditions. So this will be typically like your shear force expression, right? But you can play around with that. There's that method, and there's some condition. I don't have the time to get into that one. All right. So, all right. Any clarity you need over here? We're gonna run to another question quickly. Hello. Any question here? All right. So let's get to a question that you that we have here now. Let me jump to a different question. So as far as possible, let us walk to another question. Are you seeing my slide? Yes. Or like you are sleeping on me? Or nobody's with me? Hello? Hello?
Yes, sir. We're seeing the slide.
So we there, you know, we there.
You there? I'm not asleep.
No,
Like
we did.
people are not going on with. All right. Look at that. Look at this question. All right. I don't have I'm trying to find the original question. I didn't want to show you this question first. I wanted to all right. Let's suppose that you had this question to do, right? You never had the reactions, but now say I'm showing you the free body diagram because I don't have the original. Right? I know it's somewhere in your notes. Did I give you this problem to work? Anybody? Did you get this just question to work?
I think
Boy,
it was
sir,
done
me
in our
remember, you
tutorial
know.
class, no, sir.
Pardon me?
I think it was done in our tutorial class, I believe.
No, I don't think is this one? No, it's a different
No,
one.
it's not this one, it's a different. Yes, sir. Yes, sir.
Yeah,
True.
yeah. So, all right. I set up on a slide so I can just slide through as quick as possible. But I'm trying to remember the actual question. Hold on a second. I want to see if I have the actual one thing. If you're doing the thing I want, just to see if I have. No. This is not. All right. I don't have the question at hand. Quickly. By the way, I'm gonna try and get you guys some past papers. I'm gonna look for some past paper. This is a past paper question. I think this is 2023 stress. All right. So typically you get a problem like this. All right. Let us just discuss it with the interest of time. So you get a frame like this. The first thing you go ahead and do, you typically go ahead and get your reactions. So we see that the reaction at both G is 12.667. So everybody understand how to do this quite well, right? You're all good with this now to do your moment and all of that, right? So you would have gone ahead, you would take moment at A, then you would have to, but look, inside this section here is 2. This is, how would you figure this out? I think some measurement was given here, and I'm sure if I have all of it. When you get, this is 2. One of the first thing you could do, if you get something like this, let's say that you don't know AL and all of that. Look for the triangle that will give you most information immediately. So when I look at this, I have a triangle ACK. Look. So you have to look at your geometry. I just want to highlight something. So you look at your geometry. ACK. Now, what the information I have? I have that this is 3 and I have this is 4. So automatically I know that angle, which is regular. You can use your tan. So tan is going to be equals to the tan of theta here is going to be equals to what? 3 upon 4. Now so, all right? So it's opposite upon and adjacent. So you get that your angle is 36.9 or 87, whatever you want to use. Right? And right there, so you have this angle here. This one now, you have the same thing. So another triangle you have there, so you have 2 triangles giving information. So the first thing you need to do is jump in, look at your, say the distance between here is 2, and this distance is 3. So see it, and you can go ahead with tan again, and you say tan of 3 upon 2. So it's a tan of the angle, and 1, so it's the inverse of 1.5. So that is work out to 53.1. And if this is 53.1, you know that this is 53.1. And so these are 53.1. This alone is 36 points. So see there and there. So these are equal distance and equal height. So you know that this is 53.1. This is 53. This is also 53.31. This is also 53. So you work out all of that. And here now you just take your moment here. So this would be 4 times 2. They're using clockwise as positive, so they have 4 times 2 and they have it positive. Then this is 4 times 5. And which other one we have now? We're 8. 8 times 8. So the distance is 8 down there. So they're using clockwise as positive in this working out. And 6 is going to be times what? 10. Because 2, 2, 2 going right down is 10. And so the anti-clockwise is minus. So RG times 12. And so they are able to work out there. All right. And then they use a straight line. There's some forces in the Y. And you get that. Right. Then now they say that by method of joint, they want to find, so they use method of joint here. Right? Let's look at it quickly. So method of joints to find AL. The first force is AL. Right? So AL, you look summon the forces in the vertical, you have the angle. Right? This have 2 components, so it have 2 forces horizontal and 1 force vertical. So it's advantageous to use the vertical one first. So the reaction coming up is RA, which is what? RA is 10.33. Right? And then you have this one here, FLA, which is the sine of this angle. This one here, this component of AL. AL going up is sine. Right? So it's sine 36.87. Right? And it is positive going that way. So it's RA plus that, and you'll simply put in your value for your force. Your force here is going to be minus 10 divided by sine. When you kick it over the equal sign, so it becomes minus 10.33 divided by sine. And so you get that this is a compressive force. So instead of going that way, it's really going into the joint. So it is in compression. All right, what about the next one now? F of x, right? Going this way. How many components you have? 1, 2. So you have the cos one, which is cos FAL, cos 36.87. And that is going in the positive direction, see there? Plus this one here, AB. So AB, and we don't have AB. So we have FLA, we have AL, sorry, FAL, and you need to find AB from that. So you put in that this one, you notice you keep the sign. So you have, so it's going what now? It is when you transpose to this, you must you put in the sign with it same way, and that's a good thing. Because when you start to flip the signs, you're gonna get them wrong. So you put the minus here, you transpose to AL, this is gonna come over as minus, but this value is minus, so you put it back in the expression. I work out to 13.778 kilonewtons. So that is it. Right? Some person would tell you that once you hear that it's in compression, then you just change the sign and put it in down here. But then now, if you did that right here, so with this expression, you would certainly get it wrong. You see that? You keep your sign, work it, write your equation as you're supposed to write it, keep the sign, put it in, and it works out perfectly well with that one. All right. The next one they're trying to find now is, so that is that one, the giant. Okay. All right. Oh, so I copied it 2 times. Yeah. All right. So the second one now, you're trying to find the members going into this now. Right? So if you put it into this now, this is where you can change the sign now. Now you put it into this. So it was AL. It is not in tension, it's in compression, so it's actually going in the joint. So if you put it going into the joint, yeah, the sign, yeah, you have to observe the sign there. So it's become positive now because it's going in the joint, it's a compression. That's where the sign changed. So it's 17.22. And then now, so all I did is to take this joint here. So this is a joint you're taking. So you take the joint here and you draw it out, and you observe all of the components. So you have two components for this one too, right? So you have one coming this way, one going that way, and you have for this one, for FLK, two components, one going horizontal, one going vertical. So all you do here now, you start right here. You can write the X1 first because you have these two. So one here and one here. So it is FAL cos of the angle. The angle down here was 36.9 or 87. So you get it there and it's positive. Then this one here, FLK cos 36, and you get that value. After that, you have what? You have AL. So AL up there, and you put in AL value, all right? You transpose this, so this becomes minus. There's minus 17.22 because when you put in it, it's not this minus there, no. It's a positive value you put there, but it is minus because this come over. So it's minus AL cost, but these two will cancel. So see there, it actually come back to the same thing. So it is a compressive force. This is telling you that this one is in compression too. All right. After that, you're gonna do the vertical one. One going down, one coming up. Right? So here you have it. So this is how many forces you have here? You have one is 3. 1, 2, 3. So this one is going down, which is FLB. I think that is one you're finding. And then you have this one going up, FAL. I think it was going up, FAL, yeah. Sine 36.8 plus this other one, FL sine 36.87 equals 0. And from here, you're just simply gonna put in what you have, because you have found what? You have what you have again? You have all of these values. Am I at the right place? I jump over. So you have AL. So you put in AL value and you transpose for this guy. So everything else is going to be there, and you divide it by, hold on a second, what is happening here? Where's the expression? Well, why are we dividing here? Hold on. Is there an error here? There's an error. There's an error here. There's nothing need to divide. This is just going to come over. Alright? So there's nothing need to be underneath here. Let me look good. Because isn't this we're finding? Yeah. So nothing needed. Let me just check it good. Because see, you have this, which is that one there. Then you have this other one here going up sine, right? So it's sine. You have sine and sine. Two of them are positive, one minus, right? So there's no need for any minus here. You have AL and you have LK. So you drop in those values, right? So that's just an error, right? Honest error. So you put in the 17 point in there and put in the two value there. One is plus or one is minus. So they're saying that value, that's a zero force member. So that member there is a zero force member. That's what it's telling you right here. You go ahead and you could do the same for joint B. How many forces you have at joint B now? You have 1, 2, but remember you have one that is zero force member. So it's not in the problem. You have BK, BC, and you find most of them already. I think only, it's 2 you don't know. You don't know BK and BC. But you have AB. So you're gonna have to write the one that is more advantageous to you. Right? So if you write the vertical one first, you would have find BK first. So this look, you have to write the vertical one first. You have this value and you have that value, and you don't have this value. So if you write these, if you write the horizontal one first, you're gonna have two unknowns. You're gonna have that as unknown and this as unknown. So you write the vertical one first, which is one known, one unknown, and you simply transpose because you know this one, you don't know that one. This is sine. So it's FBK sine 56.1, and you just substitute in, you just transpose, and you get that value. Then now you go ahead and write the horizontal one, which is going to be one component positive here, one minus, right? So let's look at them. So you have AB minus and two positive. So two positive components here, and you already have BK. So you put in BK, right? And then you proceed to find the next unknown, which is BC. And so right, I'm gonna send this to you also. I'm gonna drop this in the WhatsApp so you see the workout of it. I'm trying to find the original problem. I'm gonna look for the original problem. Right, and you do the same and do the rest. So I'm gonna end it there, guys, because I think it's late and you're tired. Um, um, I still need to go through a truss properly. I'm looking for one. I have one, but this is just a guided one to help you. Fully worked out. I'm gonna look for the original problem and put it with it, so you can see what the question is asking for. So I'm gonna end it here for you tonight, because it look like some of you are really tired.
Sir, please post a record when you finish, sir.
Yeah, man, because I think you so this one here for the next part is it, guys. This section here, you would have looked on the giant and just try to look for all the unknown, right? And it's a little bit complex, which is it now? That is, which giant is that? K. So K here, so K up here, right? And the K here is where's the K? The K is right here. You would have gone ahead, identify what is horizontal and vertical again, right? Knowing everything that you work out before. So you sum the forces in the horizontal and you look for that. So you have 1 here, 2, 3. So you put the 3 of them. The ones that you work out before, you're gonna do the substitution, and work it out. It's saying that, right? So when you transpose FKC, you get 6.334, which is in tension. You do the Y now, the X, sorry. So you get 1, 2, 3. So you have them here, you put them in, and you just transpose for the one that you don't have, and you simply get the value. So you have to be very consistent and watch your sign. And then the last one would be C. C has how many forces? You have how many members here? 1, 2, 3, 4. They look at it carefully and decide which one you want to deal with first, based on what you have. And they choose to do the Y. So the Y, you have some of the forces in the Y, you have a component here, and you have one down here, and you have this one. So you simply put this one in. So you work out this already, so you have it. All right, so you have FC, but you don't have that one, and you have this one. So you simply put them in, transpose, and you get FCJ, which is this one. Then now you can write the horizontal one and the problem finish. So apparently they asked you to find a number of point forces. I'm gonna look for the horizontal, original problem here and put in it. This is a past paper question for 2023. Right? And I'll see what other past paper I can question. But in fact, I've given you some of the past paper questions already. I just didn't tell you that there are past paper questions, but you have 1 or 2 of them. I'm gonna send you another. I try look for 2023, some part of 2023. I can't give you all of it because we do reuse papers. So
Okay, sir.
right. So that is it, guys. I'm not gonna keep you any longer. It's a Sunday night. When before exam, I'm gonna have to go back and revise most of those topics, especially the vector with some of those stuff, right? I still want to do, I may have to do a truss, explain it fully. If one of those questions that I give you to work in your assignment, as soon as the assignment come in, if it's even to do a video or meet with your guys and explain it, right? Because I don't think that you all understand stress well. Maybe internal forces might be the most challenging for you, right? But the singularity method, if you know a singularity method, it's making life a little bit easier. But so I'm gonna find some diagram and show you with the singularity method. So you can attempt to use it. But the condition is what I have to make sure write out for you. Right? Because you wouldn't understand that. All right, guys. So I'm gonna finish here. Right? So I'm gonna stop share now. So we can Tuesday we'll continue with centroid before your test. So we'll finish up on that.
Before our test, which test that's, sir?
All right. The test I was planning to say that I would let you do it in the lecture period, but I've kind of changed my mind. I think I'm gonna put it online and use the lecture time to go back to some areas. But we're gonna have to still meet after the last lecture, you know, guys. Gonna have to afford me some time to go through and do some revision. So I'm gonna go back and revise clinically and mark you. The way I'm gonna revise strategically, preparing you for the exam. So remember that. All right. So everything that I've done so far is lining up for the exam, even tonight. But at the same time, I'm going to be working back with the other topics. And I don't finish, so I will finish the central this coming week. And if we finish central early in the tutorial, we can start looking at other questions. All right. All right. So that is it.
Okay, sir.
All right. Great. Have a good one. You hear?
Same to you, sir. Thank you.
Yeah, man. All right, man. Bless you.
All right, sure. Thanks.
Sure.